A vector is represented by an arrow pointing from its initial point to its terminal point. The initial point is where the vector starts, while the terminal point is where it ends. So you see here the initial point and the terminal point. All right, so let's define what a vector is. A vector V, denoted by the letter V with an arrow above it, is a quantity that has both a magnitude and a direction. So that's the definition of a vector. And the magnitude is just the length or size of the vector, and it is denoted by two vertical bars on each side of the vector symbol. And then we have the direction of the vector, which is an angle or orientation of the vector with respect to some reference axis. And the reference axis we're using is the positive x-axis. So the positive x-axis will serve as the initial side of the direction angle, and the vector itself will serve as the terminal side of the direction angle, which will be denoted by theta. So we have the magnitude that we denote with this symbol, and we have the direction that we denoted with this symbol, and those are the two things required to have a vector defined. So now let's define what a position vector is. So the position vector, which is represented by angle brackets around the two components A and B, is a vector that describes the position of a point relative to the origin. So here we have a vector, but this is not a position vector because it doesn't represent the position of Q with respect to the origin. It represents the position of Q with respect to P. So if I wanted to represent a position vector, what I would need to do is I'd need to move everything over so that the initial point of the vector would be at the origin. So how far horizontally would I need to move from the origin? Well, that would be the difference between x2 and x1. This horizontal distance from P to Q. So I just subtract x2 and x1 to find A, which is going to be the first component of my vector. In order to find the second component, which would be the vertical distance from the origin to my point, I just need to find that distance, y2 minus y1, and you notice that creates this nice right triangle here with the horizontal distance, or one leg of the right triangle, being A, x2 minus x1, and the vertical distance, B, being y2 minus y1. What I want to do is I want to transplant this triangle so that the initial point is at the origin, but I want to keep the size of the triangle the same so that this vector and the original vector have the same magnitude and direction. So because they have the same magnitude and direction, the two vectors are actually equal to each other. So the vector PQ and this position vector I've drawn, AB, which would be denoted this way, those two vectors are equal to each other. So everything I find out about vector V here is true also about the vector with initial point P, terminal point Q. So for instance, if I were to find the magnitude of the vector V, it would be the same as the magnitude of the vector with initial point P and terminal point Q. And all I have to do to find that magnitude is use the distance formula from the origin to this point AB. And that's how that's going to look there. That is just the distance formula, or the Pythagorean theorem. So the other thing we need to have to define a vector, other than a magnitude, is a direction. So we're going to use the positive x-axis as our initial side, and the vector itself as a terminal side, and the direction angle is defined as theta here. But you notice there's a triangle here, and we know we can define trig functions for the angle theta based on this triangle. For instance, the tangent of the angle theta is equal to the opposite side B over the adjacent side A. So this is what we're going to use to find that angle theta. If we take the arctangent of both sides and observe what quadrant we're in, we should be able to figure out what the angle theta is. Let's look at an example. Let the vector v be the vector from initial point P equals 6, 1, so that's this initial point, to terminal point Q equals -1, -3, so that's this terminal point, so we're looking at this vector right here. And they want me to find a position vector. The formula for finding a position vector is this. The first component, A, is just the difference between the terminal point's x value and the initial point's x value, while the second component, B, is the difference between the terminal point's y value and the initial point's y value. So for these two, that would look like this. The position vector would be the difference in the terminal and initial points x values, comma, the difference between the terminal and initial points y values. And when I do that arithmetic, I get that the position vector for this vector is the vector -7, -4. It would be this vector here. So that's the position vector for the vector with initial point 6, 1 and terminal point -1, -3. So what if I wanted to find the magnitude of this vector? I would use the formula. The formula says to find the magnitude of vector v here, I would just take the square root of the squares of the components added together. So I square each component, I add them together. When I square -7, I get 49. When I square -4, I get 16. And when I add those together, I get the square root of 65. I want to actually know what that length is. The square root of 65 is an irrational number, but I can get an approximation by typing it into my calculator. I get that the magnitude of this vector is approximately 8.1 units. So now that I have the magnitude of the vector, I'm going to go ahead and I'm going to find the direction of the vector. So I had the initial and terminal points of the vector. I found the position vector for it. Then I found the magnitude, and now I'm going to find the direction of vector v. To find the direction, I'm going to use the fact that the tangent of the direction angle is b over a, which in this case would be -4 over -7. So that I have, if I solve this for theta, theta is the arctangent of 4/7, but because I am in the third quadrant and the arctangent is going to give me an angle in the first quadrant for that, I have to add 180 because the angle the calculator is going to give me is going to be on the same straight angle as the angle I'm looking for, the direction angle. So I need to take the answer I get and add 180 degrees to it. When you type this in though, you'll get that theta is approximately equal to 209.7 degrees. Next, I want to define what a unit vector is. A unit vector is just a vector with a magnitude of 1. So here's an example. This vector right here, u1, is a unit vector. Find its magnitude. You get that the magnitude of that vector is the square root of 1/2 squared plus the square root of 3/2 squared. When I square 1/2, I get 1/4. When I square the square root of 3/2, I get 3/4. And when I add those two together, I get 4/4, which is 1. So I'm looking at the square root of 1, which is 1. So that is indeed a unit vector. It has a magnitude of 1. Notice the terminal point of this vector is actually on the unit circle. Two special unit vectors are I and j. And the vector I is a unit vector in the direction of the x-axis, and the unit vector j is the unit vector in the direction of the y-axis. Vectors can be written as linear combinations of the unit vector I and the unit vector j. So if you have position vector AB, you can also write it as the vector AI plus BJ. That is what a unit vector is. Let's define vector scalar multiplication, the scalar multiplication of vectors. So here we say that scalar multiplication involves multiplying a vector by a scalar, which is just a real number. The result is a vector whose magnitude is scaled by the scalar and whose direction remains unchanged. So for instance, let's look at the vector 2v. Well, here's the vector v, which has components a and b. If I wanted the vector 2v, I just multiply 2 times vector AB. So 2 is the scalar, AB is the vector. All I have to do is multiply both components by 2. That's how you scale a vector. If you're doubling the vector, you're doubling each component. Pretty much that's just like extending this with an extra one of itself. So on the x-axis I'd be at 2a, on the y-axis I'd be at 2b. That would be the vector 2v. So the vector 2v would be this vector right here, twice as long as vector v. It's still pointed in the same direction. All right, let's go back to vector v. If you have a scalar that's less than 1, but still greater than 0, like 1/2, well, instead of making the vector longer, it's going to scale it and make it shorter. So each one of these components gets halved, so we get a vector that's half of the magnitude of the original vector. Let's go back to the original vector v. What if instead of having a positive number that's greater than 1 or a positive number that's between 0 and 1, what if we have a negative number instead? What if we scale a vector by a negative? So let's scale the vector by -1 and see what happens. Well, that means that I'm multiplying each individual component by -1, which just changes a to -a and b to -b. So the vector -v is in the opposite direction of the vector v, but it has the same magnitude. Let's take a look at an example here. Given the vector v equals 2, -5, so those are the components of the vector, find the vector -7v. So -7v is just -7 times v, which is -7 times 2, -5. So we multiply each component by -7. That's -7 times 2, -7 times -5. So the vector -7 times vector v is the vector -14, +35. So that's how you scale a vector, and this would actually also make the direction of the vector change to the opposite direction. It would be on the same straight angle as vector v, but it would be in the opposite direction. So that's vector scalar multiplication. Let's talk about vector addition. Given vector u equals 5i plus 2j and vector v equals I plus 4j, find the sum of u plus v. So I'm trying to find the resultant vector from adding these two vectors together. So the resultant vector is just what you get when you add them, which is kind of like combining like terms analytically, but geometrically or graphically, what it is we're taking the first vector and keeping it as a position vector, but the second vector, we're going to let the initial point of that vector be the terminal point of the first vector, the one we're adding it to. Now, the terminal point of that vector is the terminal point of the resultant vector represented as a position vector. So the resultant vector is this position vector here that has the same terminal point as the new vector v. So u plus v is pretty much the same vector here, the vector 6, 6. If we wanted to get it analytically, it would be the same as just combining like terms here. So 5i plus I would give me 6i, 2j plus 4j would give me 6j. So that resultant vector, u plus v, we can get it analytically by just combining like terms. We can get it geometrically by putting the vectors tail to tip or initial point to terminal point and making that parallelogram, or that half of a parallelogram. So let's take a look at subtracting two vectors. So here I have two vectors given vector u and vector v. So what they want me to do here is subtract u minus v. I'm first going to look at the vector -v. Well, this is the vector v. The vector that we call -v is what we actually have to add to vector u to get the correct resultant vector. So u minus v is actually u minus v like this, which we can get with the distribution of that negative by just taking u and adding to it the opposite of v. So this here is the opposite of vector v. All the components are opposites. this is what the opposite of vector v would look like geometrically. It would be on the same straight angle as v, and now I'm just adding these two vectors together, vector u and the vector negative v. So to add them together, once again, I'm going to put them tip to tail. So I'm going to take vector negative v and move its initial point to the terminal point of vector u. And then the resultant vector is the position vector that has the same terminal point now as vector negative v. So I'm looking at that as the resultant vector u minus v. And if we combine the like terms over here, we should get that same resultant vector. Let's see. 5i minus 3i is going to be 2i, and 2j minus 6j is going to be negative 4j. So u minus v is 2i minus 4j, just as we predicted. So this is how you add vectors, and actually this would be a subtraction of vectors, which is just the addition of the opposite of a vector. So the next objective is going to be given the magnitude and direction, we're going to convert to component form. So here I have a vector with its magnitude and its direction, and I want to convert it to the component form. I want to know the values of a and b from that ordered pair, which is the terminal point of the position vector. I see that the horizontal distance there is a and the vertical distance is b, which form a triangle, and I know that the cosine of the angle theta here is the adjacent side a over the hypotenuse, which is the magnitude of the vector. So if I wanted to find the value of a, the first component of the position vector, all I'd have to do is multiply both sides by the magnitude to get that the magnitude times the cosine of the direction angle is equal to the first component of the vector. And of course, we can do the same thing for the opposite side here. We know that the sine of the angle is the opposite side over the magnitude. And multiplying both sides by the magnitude, I get that the second component is equal to the magnitude times the sine of the direction angle. So the component form of a vector v with magnitude with symbolized here and direction angle theta is, well, vector v is the vector whose first component is the magnitude of v times the cosine of the direction angle of v, and whose second component is the magnitude of v times the sine of the direction angle of v. So here is an example. Find the component form of the vector with magnitude 12 units and direction 227 degrees, round to the nearest tenth. Well, based on the formula, pretty direct. To find the component form of that vector, I take the magnitude and multiply it by the cosine of the angle, and then the second component is going to be the magnitude times the sine of the angle, which in this case is 12 times the cosine of 227, comma 12 times the 12 times the sine of 227. If you type those into your calculator, you'll get that the component form of this vector is negative 8.2, comma negative 8.8. Make sure you're in degree mode if you were given degrees, and you're in radian mode if you were given radians. So the next objective is exactly the opposite of the previous one. Now we want to go from component form to magnitude and direction form. We're going to use some old friends here. So for the magnitude, we're using this one, which is pretty much just the distance formula or Pythagorean theorem. And to find the angle, we're going to use the fact that the tangent of theta is equal to b over a. Here's the example. Find the magnitude and direction of this vector with this component form. So we have a is 5 and b is negative 12. So we're going to find the magnitude by using that formula, the square root of 5 squared plus negative 12 squared, which is the square root of 25 plus 144, or the square root of 169. The square root of 169 is 13, so I have that the magnitude of this vector is 13 units. Now I'm going to use the tangent of theta to find the direction angle. So the tangent of theta is equal to negative 12 over 5. We know that this vector extends into the fourth quadrant because the horizontal component is positive, which means you go to the right, and the vertical component is negative, which means you go downward, which would land you in the fourth quadrant. So because it's in the fourth quadrant, when I use the arctangent to calculate this angle, the arctangent is going to give me a negative angle. What I want is the coterminal angle that is positive between 0 and 360. So what I'm going to do is when it gives me this angle, I'm going to take that angle it gives me in the calculator and I'm going to add 360 to it to get a positive coterminal angle. When I do that, I get that the direction is 296.2 degrees. So there I found the magnitude and the direction angle given the component form of the vector. So the last objective I want to look at is finding a unit vector in the direction of a given vector. So given a non-zero vector v with magnitude symbolized here, the vector with this notation here is the unit vector in the same direction as v. So for example, if we wanted to find a unit vector in the direction of the vector we were just looking at, 5i minus 12j, well, we already know that the magnitude of that vector is 13 units. So if I wanted to find a unit vector in the direction of v, all I'd have to do is take vector v and divide it by its magnitude. That would look like this. There's vector v, there's this magnitude, and then I just break it up into two components. Then I'm going to have this as the unit vector. If you were to find the magnitude of this vector, 5/13 I minus 12/13 j, you'd find that the magnitude of this vector would be 1.